Hey, this is Brock Lemires, and in this video I'm going to introduce the capacitor. Okay, a capacitor is a electronic component, and it actually is an electrical energy storage device. And it stores electrical energy as an electric field or in the form of charge separation. So this is a passive device, and it's got two terminals on it. So before we get into like the symbol of it and the equations for it, let's just take a look at what a capacitor is or how it actually does this storage. Okay, so in the simplest form, you have a capacitor, which is two parallel plates, which are conductors. Okay, so these are conductors right here, and these, these are ideal conductors, so they absolutely can be charged up with positive or negative charge, and they can take on a lot of it. Okay, but then what you do is between the two conducting plates, what you have is an insulator. Okay, so this is an insulator, but we call it a dielectric. Okay, and that's because it is an insulator, but it has a property that allows it to essentially kind of hang on to the charge depending on what's on this plate. And let's take a look at how it does that. Okay, so number one, this insulator right here is really an insulator. Okay, so no current, no DC current flows through it. So IDC is equal to 0. It really does not allow current to flow back and forth. However, as you put charge on these plates, you can charge and discharge these plates, and in effect, you can have AC current with respect to some sort of source that sits over here. And so even though like the current doesn't actually flow through the insulating material, you can think about it in terms of like if you're going to like have a sine wave where it's like, okay, I'm going to put a little bit of positive charge there, a little bit of negative, and then a little bit of positive, then a little bit of negative, then more, then more, then more, then more, then more, then more. With respect to this source over here, the current is actually flowing over as it charges it up, and then you turn it around and you are able to like move the current this way and then put the positive charges down here and negative up here and go back and forth. So from the perspective of like if you just look at this as like a two-terminal device, AC current does flow in the capacitor. Even though the charge builds up on the plate, that's what it looks like in terms of from these two terminal viewpoints. Okay. All right. So then how does it actually store charge? Well, one of the things that's interesting is that the insulator does not allow charge to move through it. It doesn't you don't rip charge off the atoms in here. However, they do move closer to these plates based upon the charge. So for example, opposite charges attract. So as you start building up kind of positive charge on this plate right here, you will actually get the negative charge within the dielectric or the insulator to kind of start moving over into this barrier. And then similarly, when you put the negative charge down here, you'll start seeing the positive charge within this barrier or within this insulator start kind of being pulled down here. And what we call these is we call this a polarized, we say that we're polarizing the material because we're actually kind of pulling the charge within the material over to these boundaries. Now this charge doesn't rip off, but it does get pulled that way. And so this would be an example of if I charge this plate up like this, and then I came over here and I put the negative charge down here, you would actually get these polarized little dipoles is what they call them. So if I drew the same circuit over here and I kind of did this sort of thing, and in this situation, I had the same exact capacitor, but then I charged it up the other way. So I had my plus down here, plus down here, plus down here, and my negative, 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 negative down there. I would have this material here, and it would be polarized the other way. So you'd have like a plus and a minus right here, plus and a minus right here, and a plus and a minus right here. And then now imagine that this sine wave from the source is actually oscillating back and forth. And so you're kind of basically taking these polarized pairs, and when they're polarized all the way one way, when you put a positive voltage across this, they look like that. And then if you polarize them the entire opposite way, they look like this. Well, what happens when they're in between? What happens is that you can almost think about these polarized little pairs as like rotating back and forth, okay? And you can kind of think of it as either they move through each other or they kind of rotate. But the key to it all is that it doesn't happen instantaneously. So it takes time for these things to move back, okay? And that's how it stores charge. So for example, if I charged it up like this and I took this away, you would still potentially have that charge in there. It would actually hold those polarized pairs. And then if I hooked it back up again, I could then change it to look like that. And if I disconnected from it, it would in theory hold that. So it is holding electrical energy, and it's doing it by polarizing the insulating material. And all that simply means is that you pull a charge to one side of the plate using the opposite charge and vice versa. And that's how you actually store electrical energy. So it's called an electric field because you really do have, if you look at this, I mean, it really is like an electric field, right? So you have like a plus and a minus right here on these plates. And so you are able to store that by taking the material and putting the negative charges up towards just this junction and then the positive charges down here. But it really is more just like moving charge into a location within the insulator that when you take away the connection, it should stay there. Okay. Now that's a perfect capacitor. And of course, there's no such thing as a perfect capacitor. So even the best capacitors on the planet, as soon as you disconnect, they will slowly go back to having no charge on them, or said another way, having no voltage on them. Okay. So that's just in general kind of the theory of what a capacitor is. And so when you think about capacitance, you say C is the variable, the symbol that we use, and it is a measure of a material or a structure of how much charge can it hold per volt. And we give that the unit of a farad, okay? And you go, oh, farad, where's that come from? Well, that's named after Michael Faraday, okay? So one of our key scientists that came to have these discoveries, he ended up getting the unit for capacitance named after him. And 1 farad means that if you put 1 volt across a structure, it would be able to hold 1 coulomb of charge. Okay, so 1 coulomb per charge. Okay, so there it is. All right, this is the definition of what capacitance is. And this is key, right? If all you remember is what is capacitance and it's charge per volt, it'll go a long way, okay? Okay, so here's a better graphic of kind of the polarization or these little dipoles within the insulating material. And you can see that you can either visualize it kind of like this, where you say the whole material is a dipole and has been polarized. Or you can say, there's little tiny dipoles in here that all influence each other. But essentially what you're doing is you just think about, you're just taking all the charge within the material and you're moving it around. Okay, this parallel plate capacitor is one of the most common forms of the capacitor, and it actually has an equation that gives the capacitance. It's actually the dielectric constant of the material, the relative permittivity of the material, times the area of the plate divided by the distance. And you can see that it's like the further the plates are away from each other, the capacitance is going to go down. The more area you have, it's going to go up, which makes sense because you're going to have more charge on the plates. And then this epsilon right here, it's a property of the material for like how much can you polarize it and how fast or slow is it where it actually returns the charge. Okay. Now, parallel plate capacitors, one of the things you do is in order to get them denser, most capacitors, they take these parallel plates and they roll them up, and you'll see these capacitors that kind of look like cans or little cylinders. So these are examples of capacitors that you'll see like on breadboards and in circuits. So you've probably seen some of these. You see these big cylinders poking up, and you'll also see some like this where you'll have like 2 little leads on here. So here's a couple that I have right here. So this one right here in terms of the values that you see. This one is a 0.01 microfarad. This one right here is a 0.1 microfarad, and they have little codes on them that you can use, kind of like similar to resistors, where you can kind of see, you can determine what they are by reading their codes. But take a look at these relative sizes, which are correspond to like right here in this picture, compared to some of the other ones. So like here's a can or a cylindrical capacitor right here, and it's about the same size as this guy right here. And you can kind of see on it the value of this one there. It's big enough you can write on the side of it, and this is 22 microfarads right there. This bigger can right here, this is what you see typically when you open up like a computer motherboard, and that one's 4,700 microfarads. That's 4.7 millifarad. So you see right away the value of capacitance in these components is small. I mean, it's not like gigafarads, right? And so these are very small values. This one right here is actually a variable capacitor, and what it does is you actually turn that knob right there, and it'll move the plates closer to each other or further away, and you can actually vary the capacitance. But in the power industry, they do use capacitors that are much, much larger, but even those are, you know, they're measured in like a couple farads, and those are the size of like, you know, almost like transformers that you see on a distribution pole. But anyway, okay, so that's kind of the order of magnitudes and what they physically look like. So now let's start looking at the symbol for the capacitor. Well, the symbol for it makes a lot of sense. It is two lines that are separated by each other. And you have this thing where you have like, oh, capacitor, that is it right there. Some capacitors are polarized, and what that means is that it matters which terminal is which. And so that's where you see something like this, where you're supposed to connect the positive voltage to that terminal, the flat terminal, and the negative voltage to the curved terminal. So if you ever see a terminal like a capacitor like this, you can flip it either way, it doesn't matter. But if you see it like that, you have to make sure that you put the voltage on it the right way. Okay, so now we start looking at, we have the symbol, we know roughly how it performs, and now like every other device that we've looked at, we need to figure out what the IV curve or the IV characteristics are. So how do we do this? Well, like I said, if you can remember that capacitance is defined as charge per volt, we can look at this thing and we can apply some mathematics to it in order to derive what the current and voltage relationship is. First of all, Q right here, if you remember, current is defined as the change in current per the change in time. Okay, and put another way, that could be dq dt. Okay, so if you take the derivative of Q with respect to time, then that gives you your current. So if I can take this equation and rearrange it and then take the derivative of Q, I'll be able to convert that into current as long as I take the derivative with respect to time. So let's rearrange this. Let's move V over, multiply both sides by V. So now you're at C times V equals Q. And then what I'm going to do is, it is perfectly legal to take the derivative of both sides, right? That's legal, that's algebra, okay? The trick though is that which ones of these are variables that change and which ones are not. So this is not a variable, that is a constant. So that is just a number that you get based upon that capacitance. However, charge does change and voltage does change, both with respect to time. And so what I can do here is I can say, all right, so I'm gonna take the derivative of Q. So I'm gonna go like this, I'm gonna go dq with respect to time, but then I'm gonna have this over here and I'm gonna have dv with respect to time. Okay, so now this right here by definition is current. So that we can rearrange this equation and say the definition of the current through a capacitor with respect to time is equal to the capacitance times the derivative of voltage with respect to time. And this now becomes the governing equation for a capacitor. This is like the same thing as when you look at a resistor, you had V is equal to IR, right? Well, it's a relationship between the voltage and the current based upon some property about the structure itself. Well, in this situation, it's the same exact thing. It's just that this time it happens to be a differential equation. So no big deal. That's how it works. Okay. All right. So let's go through some kind of just some behavior of capacitors that, very introductory level, but we want to just kind of think about this. One of the first behaviors that pops up of this is that when you drive this with a sine wave, okay, you get a phase shift between the current and the voltage, which is always 90 degrees. And to see that, usually what you do is you do this simple test case where you say, if I put in, V of t that I'm going to have across that capacitor, and this is across the capacitor, right? And I'm going to say it is sine of 2 pi ft, and there it is. Okay, so that's some sine wave that is across the capacitor. And I'm going to go ahead and find what the current is. So I take the derivative of this, right? So I take the derivative of VC with respect to time. And then what I do is I take the derivative of this. And so when I take the derivative of sine 2 pi ft with respect to time, what happens is you remember that the derivative of sine is cosine. Okay, so I actually get cosine, but then it's also the derivative of what's inside too. And so when I have 2 pi ft with respect to, you're taking the derivative with respect to time, so what you end up with is just the constant right here. So you're going to have cosine of 2 pi ft multiplied by 2 pi f. Okay, so that's what came out there. And then where did the c go? Well, it's right here, right? So it's the I is equal to dv dt, which was what I had right here, and then I actually had a c out front, so I have to remember to multiply this by c. Okay, so that's a really sloppy way of saying this. IC with respect to time is equal to, and then you're going to have this constant out here. You're going to have 2 pi f c multiplied by cosine 2 pi f t. Okay, now why was that important? It's because take a look at this. This is the current through the capacitor. This is the voltage through the capacitor. Notice a couple key things. Number one, the frequency argument, okay, or what is the argument that you plug into the cosine and sine is exactly the same. That means they have the exact same frequency and period. Well, that's what we've said about circuits. Nice. Well, also look at this. Sine and cosine, they are just flat cosine. They're just shifted versions of a sine, and then of course the current is scaled. So why that's important, that's not why it's interesting, is because if you plot this now, if I plotted a voltage, okay, so this is going to be my V of t across the capacitor, what my current would look like is a cosine. So it'd kind of look like this. It'd look like that. And so we say, well, there's a phase shift between these. And the phase shift between them is going to be 90 degrees. So now you go, well, okay, if this is my current with respect to time, there's a 90 degrees phase shift between these two signals. Okay, the crest to the crest is 90. The crossing to the crossing is 90 degrees as over one cycle, right? Remember, this is 360 degrees. And so you say, well, who leads and who lags? So who leads versus lags? So in this situation, the current actually crests before the voltage. So we say that the current leads the voltage in a capacitor by 90 degrees. Okay? And to remember that, what you can do is use this acronym, this ICE or ICE. And so the current in a capacitor is before the voltage. And you're like, where's the E coming from? Well, E stands for electric field, or E is what voltage is used like. Well, E is the variable that physicists use, but you're going to go, well, it's electric field. Okay, so the electric field. So as long as you remember ICE and you remember that it's always a fixed 90 degrees, you know the current or the phase shift between a capacitor in terms of its current and its voltage. All right, so let's do another quick little example of how this thing behaves. And so if you look at this equation, the voltage cannot change instantaneously across the capacitor, but the current can. And if you just look at that equation, you can if you just look at the operation of it. So the whole thing that a capacitor does is it prevents the voltage from instantaneously changing because you polarize the material, and then when you try to change it the other way, you have to overcome the energy that's been stored in the capacitor. So you can't change it. It's just by design. That's how a capacitor works. The current, though, absolutely can change. In fact, it can change quite rapidly because it is proportional to the rate of change of the voltage with respect to time. Now, where you see this would be in a circuit like this. So if I came along and I hit this with like a step, is what we call it, and I'm in a resistor capacitor circuit, okay? Just like a diode, you never have these things by themselves. So if I had a resistor diode, and I'm going to look right here where this is like plus or minus VC of t, and I plotted this, okay? So I plotted this versus time, and I hit it with this step like this. So I go, okay, here's a time, and I'm going to come along, and I'm going to go boom. So this right here is V in with respect to time. Okay, so that's what this is, V in. All right, so then what does the capacitor look like? Well, if it's at 0 to begin with, what's going to happen is it will slowly ramp up and finally reach this value right here. Okay, so this right here is going to be V of C of t, and it just has to do with you can't change the current you can't change the voltage instantaneously. Now, it turns out that the profile of this ramp is actually an exponential, so it's e to the negative t over RC. So it actually has to do with this relationship. So if you're falling, right, if this went down and you went like this, you'd use this equation to describe the exponential decay. If you're ramping up, you would use the, the V final, minus V final times this. And so depending on which whether you're going up or down, you would use the corresponding equation, but it doesn't matter. All that really matters is that the value of the capacitor and the resistor dictate how fast or slow it ramps up, okay? Current, on the other hand, can change instantaneously. So if I plotted current on here, what would happen is you'd get this huge spike of current and then it would ramp down like that. So this would be IC of t. Okay, so that's just the behavior that you see when you look at it versus time. All right, so the last thing that we look at with capacitors is how it behaves in terms of its resistance, effective resistance, when it's at a low frequency versus a high frequency, okay? And so consider for a second that I have a circuit that looks just like this, and I'm gonna drive in a sine wave, right? And what I wanna do is I wanna plot across frequency. Okay, and so it's like this is kind of a new way of looking at things, right? Usually we have time on the independent axis, but now what I want to do is I basically want to come in here and I want to put in like 0 hertz, right? This is in hertz, and then like 1 hertz and like 10 hertz and 100 hertz and 1,000 hertz and do kind of like this log scale of different frequencies. But what I'm doing here is I'm basically putting in like DC is just flat. And 1 hertz is going to be this really slow sine wave. Then it's going to be like faster sine wave. Then it's going to be really fast sine wave. It's going to be super fast sine waves and super fast sine waves. And this is what my input is going to be. So this is going to be Vs in this circuit, okay? And what I want to do is at each given frequency, I want to see like what comes out of this thing, all right? So what does it look like when you're at DC versus you're at what we call a high frequency, okay? So HF or high frequency, okay? Well, really, you can kind of determine this by looking at the equation itself. So if I have IC is equal to C dV dt, dV dt has to do with how fast the voltage is changing with respect to time. So if I am at DC, there is no change in voltage with respect to time. Okay, and so this is 0. Okay, so dV dt leads to this component being 0 because there's no change with respect to time. Why is that interesting to us? Because that means that there's no current flowing through the capacitor. Why is that interesting? It's because if there's no current flowing through it, it looks like an infinite impedance, or said another way, an open circuit. So I could actually redraw that circuit just based on this equation, and it would look like this. I would have like nothing there because no current is allowed to flow through there based on the equation. And that's how it is, right? And so this is kind of cool because you can still absolutely have a voltage that develops across an open. It's just that you don't have any current flowing. So what that means is that if you put in Vs in this circuit, what you would get across the capacitor is Vs. Okay, you would get the whole thing right there. All right, and it's like, okay. So we say that at DC, a capacitor looks like a open circuit. So it has infinite, it's basically its resistance is infinity, and we haven't covered like what it means to vary with the frequency to vary with respect to frequencies. We're just going to leave it as R. For those of you who have studied this would be impedance. But anyway, right now we're just talking about its resistance is an infinite when you're at DC. Okay, and now you go, well, okay, what about when it goes up to what we would call high frequency? So where you're just going really, really fast. Well, what does it mean to go really, really fast? What it means is that the voltage across the capacitor is moving quickly, or it has a very high dV dt. So you could almost come in here and say, well, dV dt would almost be infinite. So now what does that mean? Why do we care about that if this dVd term is huge as you get to a very, very high frequency? Well, it means that the IC is going to be nearly infinite. Okay, and now you go, I don't understand. How is that even possible? Well, what that means is that this capacitor could essentially take as much current as you would give it. That means that at high frequency, basically the capacitor looks like a short circuit. It looks like a wire. And you go, interesting. That's kind of interesting because is this circuit going to pull infinite current? That's like, absolutely not. You never put these things alone. So what would happen here is you would limit the current with the resistor. But the capacitor itself would essentially have a resistance that's equal to 0 at high frequencies. Okay, and so if I drew that, kind of did the equivalent plot like I did over here of this circuit, what I would have to redraw my circuit as is this. I'd have a resistor, and then I basically have a short circuit. I just have a wire there, and I would still be looking right here and going, what is VC of T? What is that? Well, if you have a short circuit, you have 0 resistance, you cannot develop a voltage. So that means that out here, you are going to have 0 volts. And so this is kind of interesting because then as I put in VS out here, when I get out to this high frequency, you're going to basically be down here to 0. And as you go higher and higher in frequency, what happens is that is what you see on a capacitor. You will actually essentially short out the voltage as you get higher and higher in frequency, and the capacitor looks like a short. So to summarize that, when we remember the behavior of a capacitor, what we remember is this. At DC, the capacitor looks like an open circuit. So you just basically can model your circuit like that. But at high frequencies, it is going to look like something like this, where it's a short. In between, what does it look like? That is the topic for another video because that gets into like the material science and the circuit behavior and imaginary numbers and all that sort of stuff. So we're not covering that. We're just giving a high level overview. Why this is so important is because this frequency response behavior can be used to make a circuit which is called a filter. Once again, that is a topic for another video. But anyway, that is the behavior of capacitors. They're very popular, not popular, they're very useful in electrical engineering. You're going to see them throughout your entire career. All right, that is it, and see ya.